Hello everyone, in this lecture we are going to calculate the Coulomb barrier potential when the two nucleuses making fusion they feel. First of all, let's know why the Coulomb barrier potential is important during fusion. In general, we generate electricity from fission because it is more preferable, but in fission there are some risks. There could be uncontrolled chain reaction and can make a disaster, although it can produce lots of radioactive elements which harm the whole environment. That's why fusion is not preferable. We are going to make fusion reaction which would be much eco-friendly for our environment, and in fusion reaction, there will be no production of such kind of radioactive elements. If produced, they will be decay away in few years, and those are not so much harmful as compared to fission. But to do fusion, we need some amount of energy, because in fusion we combine two bare nucleuses, two positive charges to became one. As positive charges, any like charges repel each other. That's why when two nucleuses are brought together, they repel each other. They don't want to become a single particle. They always try to be its own, and they feel some sort of Coulomb barrier. To overcome this Coulomb barrier, we provide kinetic energy to this particle so that they can overcome the barrier and become such a small distance when there will be no force of electromagnetic field, and there will be only interaction by nuclear, or I can say strong nuclear force. To make to these nucleons such a small distance, we need the kinetic energy, and to provide kinetic energy, we need external power sources, power energy. Those energies can be provided by confinement processes. Inside sun, the gravitation provides that confinement energy, and in our experiments, in our laboratory, we do confinement using magnets or using lasers. If we use magnetic confinement or magnetic field to make fusion, we said it magnetic confinement. And if you use lasers to make fusion, we called it inertial confinement. And we can use magnets and lasers simultaneously. In that case, it's called magneto-inertial confinement. Although these processes are in theory, in general, in practical case, we are unable to create energy from fusion reaction. Then it takes energy to accelerate the particles or to combine two nucleuses, but the energy it takes it more compared to energy produced during fusion. That's why in our present time we can't make electricity from fusion reaction. So let's calculate what amount of Coulomb potential two nucleuses feel when they close apart. To do that calculation, we assume two assumptions. That first assumption is nucleus is spherically symmetric object. As it is spherically symmetric, we can define a radius for this sphere given by small r1. So this nucleus having radius r1 have mass number a1. So that's our first assumption. It is a spherically symmetric object having radius r1, and this r1 can be written as r0 a1 to the power 1/3. That formula you may learn in basic physics class. And our second assumption, the other nucleus with which this nucleus will fuse have the radius small r2, and r2 can given by r2 equals to r0 a2 to the power 1/3, and the second nucleus is mass number given by a2. So our second assumption is these two nucleuses which will fuse are touching each other with their surfaces. Now let's calculate the Coulomb barrier potential in this case. We know Coulomb force Vc is given by charge between these two nucleuses. So in this case, let's assume the charge is given by Z1e, and in this case charge is given by Z2e. So charge Z1e times Z2e divided by 4 pi epsilon naught times distance between the center of these two nucleuses, which is R1 plus R2. So this is the Coulomb force these two nucleuses will feel during the fusion process. If you further simplify this, because this E square divided by 4 pi epsilon naught have a standard value which is 1.44 MeV, and this R1, R2 can be expanded by this formula. So we have final expression for Coulomb barrier potential given by 1.44 divided by small r0. If you take common small r0 and put the value 1.2 Fermi, so this is MeV Fermi. The value of E square divided by 4 pi epsilon naught is 1.44 MeV times Fermi. So let's put this MeV, mega electron volt, time Fermi. This Fermi get cancelled out, and other terms are A1 to the power 1/3 plus A2 to the power 1/3. And we have Z1 times Z2. That is, our expression for Coulomb potential can be written as, instead of this E square, we can write 1.44. This R0 is 1.2 Fermi. This Fermi get cancelled, and we have Coulomb barrier potential given by A1 1/3 plus A2 1/3 Z1 times Z2 mega electron volt. This is our expression for Coulomb barrier during fusion. So if kinetic energy provided externally greater than this Coulomb potential, fusion will occur, and if it's not, there will be no fusion.